Hello, my name is Sergio Garcia. This is my video for the test going over chapter 1, which goes over vectors. I'm going to quickly go over the adding and subtracting of vectors first, and then I'll eventually go over and summarize dot product and multiplication of vectors. To my left, I have an example that I pulled from the book that I feel like really comes in, like represents all there really is to know about adding and subtracting vectors. So we're going to quickly go through that, and then we'll eventually get to our second example. So in this example, we are going to be both adding vectors, subtracting vectors, and then we're also going to be finding their the magnitude of their angle. So I guess the first way we can go is just get started. With anything like this, we should first look at what the question is asking. The first question we're given is, what is vector A plus vector B? When answering a question like this, it's always important to understand how vectors work. And the best way to do that is by breaking them down into components. Let's first look at our vector A. We can see that it has an x component of 0, right? Because it moves 0 direction. It's on the y-axis, so it's x component. A of x is equal to 0. And if we look, it moves in the y direction 8 times down, right? So it has an A of y component of -8, correct? That means that vector A is equal to 0i plus, or hold on, you can do minus because it's negative, minus 8j, right? That is our vector A. And we can do the same for B, albeit it's a bit more confusing, so I'm going to walk you through it. So for B, we actually need to use trigonometric functions to find our B. So if we look at B on the graph, we can see that it's not on any type of axis, be it y or x. So we need to use what they give us. So we know that B is 30 degrees to the right, like off of the y-axis. And we know that B is 15 meters long. With that, we have both our angle and the magnitude of the line. What we can do with that is we can set up a triangle so that we can use trig identities from our SOHCAHTOA to find the magnitude of its x and y component. So this would be b of x, and this would be b y, right? You can see how it's pretty simple. This is, you have to go in this direction, y amount, and then x amount to get to where b is, right? So we travel in the y direction this much, and the x direction that much to get where b is. So if we were to do this, we look at our angle, right? That's how we set this up. And we see that if we want to get b of x, that's the opposite line of the angle. So since we have the opposite line, we would set it up like this. It'd be using the sine in SOHCAHTOA, right? Sine is opposite over hypotenuse. So the way we'd set up our equation to find b of x is we would have opposite equals to hypotenuse times the sine of the angle. So that would essentially equate to 15 times sine 30, which if you plug that into your calculator, like I'm doing right now, would equal to 7.5. Right, so that is our value for this. B of x will equal 7.5, this line right here. And now for our b of y, we run through a similar process. Our b of y is the adjacent line to our angle. So if you know SOHCAHTOA once more, the adjacent is associated with cosine. So we'd end up doing 15 times cosine of our angle, which is 30. And we will plug that into our calculator once through, and we will get 13, an even 13. Beautiful, beautiful. That means that our angle oh, not of A, whoopsie. Our angle of B, I'm sorry, our components of B are going to be 7.5 in the I direction plus 13 in the J, right? So this is 13 up and this is 7.5 to the right. I'm going to start erasing some things just to make some room. I'm just going to bring these over. Actually, I'm going to erase this. Actually, no, I'll keep it. No, I'm going to erase it. And I'm going to quickly select these. Forgive me while I do this cleanup. It's going to be up here. So now that we have our A and B, we can answer some questions. So let's say they were asking us to do A plus B and not only to find the magnitude, but to find the direction as well. So how we would handle that, first we look at A plus B, and we would automatically know that the way we could handle it is by adding components. So we would have A of X plus B of X plus A of Y plus B of Y. Now, if we actually do that, we'll get, in a different color, 0i plus 7.5i plus negative 8j plus 13j. If we add that together, that's going to be 7.5i plus 5j. Now that we have that, we can sort of set this up as like its own little triangle. So let's say we had, what's it called? A graph, right? We have our own little graph. And we were moving 7.5 in the I, which is the X direction. And whoops, and 5 in the J direction. Now, since we have those two lines, we can set up a new line that is the hypotenuse of these two lines, right? And we can call that R. Well, this is 5 and this is 7.5. So how do we find R? Well, we know it's the hypotenuse of these two angles, right? So we can use a variation of the Pythagorean theorem to calculate it. So R, in this case, would equal to 7.5 squared plus 5 squared, and then do the square root of that. So it would equal to 9 meters. On top of that, we now have to find our, in a different color, our angle right here. We'll call it X of R, right? So we know the magnitude now. We see it right here, it's 9 meters. Now we need to find in what direction is R going. Well, the simplest way to do that is to use tangent inverse, right? So we're going to be using the TOA part of SOHCAHTOA. The way we're going to set this up is we both know our opposite and our adjacent angles, correct? They're right there. 5 is our opposite of X and 7.5 is our adjacent. the way we would handle this is by having tangent inverse of our opposite, which is 5 over 7.5. And if we plug that into our calculator, we would get about 34 degrees. So we can say that x is 34 degrees off from like the x-axis. And that means that our total answer for A plus B with magnitude direction is 9 meters at 34 degrees. That's how we play ball in this situation. But we can pull up another example. Let's say they were asking for A minus B, right? Let me get my eraser. Scrub this down. Well, it's a similar process. If we have A minus B, that would equal to A of x minus B of x plus A of y minus B of y. So in this instance, we can just add them together really quickly. It would be just quickly substituting your values, 0 of I minus 7.5 I plus negative 8j minus 13j. Oh, that is not a 3. 13j. So if we equate that together, we're going to have negative 7.5 I minus 21j. And now that we have that, we can set up a triangle. Of course, we should first always draw our graph because that'll help us with our angles, and you'll see, especially in this example. So if we draw a graph, such as this one, we can now formulate a triangle where we move negative 7.5 in the I direction, which is the x, right? So negative 7.5. And then we go down 21 because we're moving in the negative j direction. So 7.5 negative 21. You see how this is different from the last one? Before we were working in the first quadrant, but now we're working in the third, I believe, which will affect how our angle is computed, but I'll show you that in a second. So we want, firstly, the magnitude of R. And remember, we find that with a Pythagorean identity being negative 7.5 squared plus negative 21 squared. And if I plug that into my calculator, we are going to get 22 meters. So now we know that our magnitude of R is 22 meters, which is great. Now we have to find the angle of X. to find out in what direction exactly r is going in those 22 meters. So if we look at our two things, we remember TOA and SOHCAHTOA, we have our opposite, we have our adjacent, right? So we have to do tan inverse of those two things. So tan inverse or arctan, whichever you'd like to call it, they're both the same. I like to go call it tan inverse of negative 21 over negative 7.5 is equal to, well, let me plug this in my calculator. And that equals okay, so that's going to equal to, sorry that took so long, I was having calculator issues, to about 70 degrees, right? So x would be about 70 degrees. However, we need to keep in mind that instead of being off the 0, like last time in quadrant 1, it's off the line 180 degrees, right? So this is 0, this is 90, and that's 270. This is essentially, x is going to amount to 180 plus 70 degrees, which equals to about 250 degrees. So x in reality equals to 250 degrees. And that makes sense because it's around in between 270 and 180. So that's essentially how it works. Instead of on the last one where it was just flat out 34, since it was in comparison to the 0 direction, since this is 180, you need to take your tan inverse and place it in respects to the two lines it's in between, being 180 and 270. I alternatively could have also subtracted. If I used a different angle, I would have gotten 20. And then I could have done 270 minus 20 to get 250 as well. So either way, the angle for this specific magnitude is 250. So our A vector minus our B vector is equal to 22 meters in the 250 degree direction. All right, so that's the general examples for vectors in terms of magnitude and direction. The next thing I can show you is now how to multiply vectors, which is essentially called like a dot product. So it's a bit different, admittedly, but it's pretty effective to know. So let me clear my board. It's gonna erase a lot of things. Such colorful lines. I'm actually going to pause the recording and I will come back when I am finished resetting up. Okay, now that we're back, I have everything set up so we can talk about multiplying vectors as well as, dot values. So we're going to do our quick little multiplication for dot products, and I'll sort of explain how it works. So first thing, if we just ignore everything else, if we look at the right side of my screen, when you have two parallel vectors that are going in the same direction, right? They're parallel to each other. The best way you can look at it is they just multiply automatically. So let's say this is 5 and this is 10. if you multiply these two vectors, you will get a vector that's 50. It's also important to note when you multiply vectors, there is no unit assigned to it. So if these were like 5 meters and 10 meters, your answer will just be 50. No meters involved, just 50, which is a really weird thing to think about, but that's just how it works. There's no unit of measurement assigned to a dot product. So I can show you a couple examples of non-parallel lines, because again, parallel is just straight up multiplication. When you have a non-parallel line, you actually look over here. This is an equation that can always give you the dot product of two non-parallel lines. I mean, it even works on parallel, but like you don't like need it to. So let me explain it. So vector A times vector B, these are any two vectors, equals to the magnitude of A times the magnitude of B times the cosine of theta. Theta in this case is the smallest angle in between the two vectors. So if we go to our first example here, it'd be this one to our left. We see that it's vector A times vector B. So if we were to just do that, right? So vector A times vector B is going to equal to, what's our magnitude for vector A? That is 3 times our magnitude for vector B, which is 4. Now we look at the angles between them. The smallest angle we can see, there's two angles we can use. We can use this angle, and then we can use this angle. Now it's, you can decide to yourself which one's bigger or smaller, but I'm pretty sure I would go with the green angle. So if we tackle that, we see that this angle is from 0 degrees to 60 degrees. 60 minus 0 is 60, right? So it'd be the cosine of 60 degrees. Now, if we multiply that all together, that's 12 times cosine of 60, which is going to equal 12 times 0.5. Our dot product is going to be 6. Let me write that better. 6. Still not better. 6, whatever. It's really hard to write the way I'm writing. So our dot product for the multiplication of these two vectors is 6. And yeah, I mean, that's how I play the game. Obviously, there's better ways to understand it. You kind of just understand that you're multiplying A times the X portion of B, because that's parallel, but this equation just works, right? So your answer is 6 for the dot. And remember, there is no meters. This is not 6 meters. It is just 6 for your dot product. So we're going to do the next one. In this case, these two arrows are pointing perfectly against each other. Both of them are at 0 degrees. I'm sorry, hold on. This is 180 degrees. And this one is at 0 degrees. Right? So these are going in opposite directions. So how we would tackle that again is A times B equals 3 times 4. And this angle right here is, 180 minus 0. So it'd be the cosine of 180. So if we do that, it's 12 times, we know the cosine of 180 is -1. We would get -12. Yes, perfect. Looking at my notes, that is perfect. It's -12. Now we're going to do our third example. Oh, I forgot to write a magnitude and direction for this one, so let me fix that. This will be 3. It's equal to 3. And the 0. Okay, so let me switch back to my green color. So this one is a bit trickier. We look at this and we see that, first of all, we have our equation, right? So it'd be the magnitude of A, which is 3, times b, which is 4, times the cosine of an angle that is the smallest one between the two. So the wrong thing to do here that a lot of people could probably mistake on is using the angle 60. That is not the right thing to do, because that is not the angle between these two lines. That is the angle between this x-axis and 4, right? That's not that helpful. The two angles we should be looking at are this one as well as this one. Now, if you ask me, the green one is smaller. So how do we find the green one? We look at this and we know that this right here is 90 degrees. Correct or incorrect? I think it's correct. And we know that this is 180. So we find that 180 minus 60 degrees, 60 degrees is equal to 120 degrees. So we know that this line is at 120 degrees. So since A is at 0 degrees and this is at 120, 120 minus 0 is 120. So we use the cosine of 120 because that is the smallest angle in between the two. And if we plug that into a calculator, what we're going to get is 12 times negative 0.5, which is equal to negative 6. And that's our answer for that one. Now we'll look at our final example. So we've said before that dot products essentially work best. Dot products work the best when you are multiplying two parallel lines, because you just flat out multiply them, right? You don't need to do anything special. If you have a parallel line that's 3 and a parallel line that's 4, you multiply them together, you're going to get 12 no matter what. In this situation, where you have two perpendicular lines, right? There's a 90-degree angle between the two. I mean, that kind of spoils how we're going to do this, but I'll show it to you. So if we do, oh my God, it looks like a triangle. There we go. Vector A times vector B is going to equal to the magnitude of A, which is 3, times the magnitude of B, which is 4, times the cosine of 90 degrees. Now, you don't need to be a trig expert to tell me that the cosine of 90 is 0. So 12 times 0 is equal to 0, which means that the dot product of these two perpendicular lines is 0. And that works for every single perpendicular line, no matter what the magnitude is. It can be 1,000,000, it can be 2, it can be 1.5, it can be any number. No matter what, if you take the dot product of two perpendicular lines, it will always amount to 0. And that's essentially everything I would go over in chapter 1, just knowing how to add and subtract vectors as well as multiply them. Oh, just one small thing before I go. When you multiply a vector times a scalar, for example, what you would do is, let's say it's 3 times vector A, which equals to 7. You just flat out multiply that as well. So if you have this equaling to 7, you would eventually get 1, 2, 3, where these all equal 7, which equals to 21 vector length in meters. And you don't cancel out your magnitude, so it'll always like have a number to the side into it. It would just make the whatever vector you have 3 times larger in this case. And yeah, that's everything essentially when it comes to adding, subtracting, and multiplying vectors. Thank you.